Okay, brings us to applying all transformations to sinusoidal functions. Y equals a sine of b times theta minus c plus d. Or y equals a cosine of b theta minus c plus d. This is your general form for sinusoidal functions. Remember, instead of a, b, h, and k values, now we have a, b, c, and d values. Absolute value of a is the amplitude. B changes the period in our sinusoidal function by using the formula 360 degrees over b, because remember the standard sinusoidal function, y equals sine of x or y equals cosine of x, is 360 degrees or 2 pi, but then that period changes by dividing by absolute value of b. C is the horizontal phase shift. This is like your h value. And d is your vertical displacement, which is your up and down movement. Okay. Other formulas: amplitude equals the maximum value minus the minimum value divided by 2. Also, d, the vertical displacement, this is the maximum value plus the minimum value divided by 2. Okay, other formulas: the maximum can be obtained by using the formula d, which is your vertical displacement value, and adding it to the absolute value of the amplitude. Likewise, the minimum can be obtained with the formula d, the vertical displacement value, minus the absolute value of the amplitude. Okay, let's do a couple of examples. For each function, state the parameters a, b, c, and d, then state the amplitude, period, phase shift, and vertical displacement of each function. Y equals 2 sine of 3 theta minus 30 degrees plus 1. Well, absolute value of a equals 2. Hey, I should start with this, folks. Remember, I'm always big on stacking these equations, so y equals a sine of b theta minus c plus d. Okay, so the absolute value of a equals 2, so therefore the amplitude is 2. The b value is 3, so we're in degree mode, so period is equal to 360 degrees divided by the absolute value of 3, and that equals 120 degrees. C, that's the phase shift. That's 30 degrees. So the phase shift is 30 degrees right. D, which is the vertical displacement, that equals 1. So the vertical displacement 1 unit up. Okay. Next one. Let's stack the two equations. Y equals a cosine of theta minus c plus d. Well, this is not in that form, so we need to make it into the form. So y equals negative 3 cosine. Let's factor out a 1/3. That's theta minus, theta plus, how do I get a pi over 6? I need to factor out a 1/3. So 1/3 theta plus pi over 2. Okay, and then minus 4. Now my equation is in the form y equals a cosine of b theta minus c plus d. So what's my a value? Absolute value of a equals absolute value of negative 3. That equals 3. So the amplitude of the sinusoidal function, amplitude, is 3. My b value is 1/3. So my period, remember we're in radians, folks. Okay, so period equals 2 pi over 1/3, absolute value 1/3. And then that's a period of 6 pi. My c value, negative pi over 2. That's a horizontal phase shift, pi over 2 units. This is to the left. Okay, and then my d value, vertical displacement, equals -4. So that's a vertical displacement 4 units down. Okay, B. Sketch y equals 2 sine of 3 theta minus 30 plus 1 over 2 cycles on the grid below. Do not use your calculator. Let's use method 1, which is using transformations and mapping notations. SRT still applies. So in black, I'm going to sketch my standard sine function. So base function, folks, is y equals sine of theta. So 0, 0, 30 degrees, 1/2, 60 degrees, square root of 3 over 2, maximum at 90 degrees, and then these values repeat. So we know how to graph this. Okay, over 2 cycles. So 1. Okay, we can only fit 1 cycle on this one. Okay, so this one, let me make a dotted line, folks. There we go. So this one, y equals sine of theta, our base function. Okay, let's start mapping out our different transformations going on. So if I have y equals 2 sine of 3 theta minus 30 degrees plus 1. We got all the different transformations going on. So I have it in the form y equals a sine of b theta minus c plus d. Remember, it's easier to eat pancakes when they're stacked, so it's easier to read equations and functions when they are stacked. So my a value, absolute value of a, is absolute value of 2. That is 2. So that is my amplitude. Okay, you got that? B value is 3. So my period, okay, so it's not the factor, it's called the period now for sinusoidal functions. We are using degrees, so that's 360 degrees divided by the absolute value of 3, and that equals a period of 120 degrees. Okay, C value, that is 30 degrees, so that is a horizontal phase shift, 30 degrees right. Okay, and lastly, d equals positive 1. That is a vertical displacement 1 unit up. Okay, so based on all of these transformations, let's do this. XY. So I'm going to start a chart here. Let's go function XY, the original base function, and I'm going to transform it to remember this handy thing. Instead of H here, I'm going to put C. A, Y, instead of K, I'm going to put D. Okay, so what does this look like? XY transforms to X over B, which is 3, plus C, which is 30 degrees, times A, which is 2, Y, plus D, which is 1. So all the points on the black graph get transformed to the new mapping notation. Okay, so method 1, we're using transformations and mapping notation. So let's try 0, 0. So I'm going to try a whole bunch of points here. Let's just try the first 1, 2, 3, 4 points, perhaps. Or let's do the easy ones. 1, 2, I'm going to do 0, 0. So what does that transform to? That's 0 over 3 plus 30. And that's 2 times 0 plus 1. Well, this is just 30 degrees and 1. Okay, so see how the math is done? I'm going to just erase it and replace it. So 30 degrees and 1. So 30 degrees and 1. You see how that works? So 30 degrees and 1 is right here. Okay, next one. Let's go 30 degrees and 1/2. So that x value, that's 30 degrees divided by 3 plus 30 degrees, comma, 2 times 1/2 plus 1. Well, that is 10 plus 30 degrees. Okay, comma, 2 times 1/2 is 1 plus 1. So that's 40 degrees, comma 2. So 40 degrees, comma 2. So that's 45 is about here, 40 degrees, comma 2, right about there. Okay, so that's 42. I'm going to just replace it with 40, comma 2. Okay, there's our second point. Let's do one more at the maximum at 90 degrees. So at 90 degrees, our base function, 90 degrees, we're at 1. So what does that look like? So that's 90 degrees divided by 3 plus 30 degrees, comma, 2 times 1 plus 1. So that becomes 30 degrees plus 30 degrees. 2 times 1 is 2 plus 1 is 3. So that ends up being 60 degrees and 3 for our transform point. So 60 degrees and 3. Okay. So 60 degrees and 3. Okay, next one, 20, 150. Let's go 150 and 1/2. That's 150 over 3 plus 30 degrees, comma 2 times 1/2 plus 1. So that's 50 degrees plus 30 degrees, comma 1 plus 1. That's 80 degrees and 2. So 80 degrees and 2. So right about there. Okay. Okay, and let's do one more. 180 degrees and 0. So that's 180 degrees divided by 3 plus 30 degrees, comma 2 times 0 plus 1. That's 60 degrees plus 30 degrees, comma 1. So that's 90 degrees and 1. 90 degrees and 1. Okay. Okay, so let's write that in. Okay, so you can see a nice little pattern developing here. I'm going to go ahead and plot the rest of these points. Okay, so right about there, I need 2 full cycles. Okay, let's go a little bit more than 2 cycles here. Okay, I think that's enough. So let's go draw this in. Okay, this is our transform function using nothing but mapping notation. Okay? Alright folks, over on Desmos, we're going to sketch 2 sine of 3 times theta minus 30 degrees plus 1. First, let's start with the sine function. Okay, so we see our typical sine function, maximum at 90 degrees and 1, minimum at 270 degrees and -1. We're going to apply a value. So this one, I'm going to do one transformation at a time. So when I apply an a value of 2, we expect the amplitude to double. It's a vertical stretch factor of 2. So right there, okay, so you can see the amplitude double here. So 91 goes to 92. Okay, let's stick with that one. Now, I'm going to apply a b value of 3, which is which relates to a period of 360 degrees divided by absolute value of 3, which is 120 degrees. So we should see the period shrink by a factor of 3, or like 1/3, right? So it's multiplied by a factor of 1/3, all the degrees. So watch what happens for a b value of 3. Okay, as we expected, this key point 92 come on. So there's 92, and that transforms to 32. So that 90 degrees got divided by 3, which is what we expected when we thought about the period going from 360 to 120. Okay, so one full period is all the way up to 120 now. Okay, so let's start with that one. So I'm going to get rid of the old one, the red one. And then now I'm going to apply a horizontal phase shift of 30 degrees to the right. So what do I expect with the blue graph? It's going to move to the right by 30 degrees, and that's what we see from 0, 0. So 0, 0 here to 30, 0. Okay, 0, 0 to 30, 0. Likewise, 32 to 62. Okay, so the last part we're going to do is we're going to do a vertical displacement, a d value of 1, which should move it up. And there we go. It moves it up 1 unit. So instead of 62, it is now at 63. Okay. And then our final function looks like this. And then our d value, maximum plus the minimum, divided by 2, the vertical displacement. Maximum of 3 plus the minimum of -1. 3 plus -1 is 2. 2 divided by 2 is 1. So our vertical displacement is 1 unit up. So we measure the vertical displacement from the sinusoidal axis. It used to be at y equals 0. So if we go to y equals 0, there it used to be there. And that's our original sine function here. Okay, but then it moved up. So I'll leave that there. And then it moved up to y equals 1. And that's from our equation d equals maximum value plus minimum value divided by 2. Okay, method 2 for sketching this transformation. So this is the same transform function, except I'm using radian values. Okay, so you'll notice the transformation, they're the same, except this is in radians. So let's get some practice using radians. Okay, so quick review here. I'm going to put this into the form y equals a sine of b theta minus c plus d. So my a value, amplitude, is 2. My b value equals 3. C value is pi over 6 radians. And then the d value is 1. Okay. My sine graph, let me plot the major points here. Some of it got obscured here. So this is pi over 2. 2, 3. This is pi. 1, 2, 3. This is 3 pi over 2. 1, 2, 3. This is 2 pi. Okay. Let me just get rid of some of this here. Okay. Let's draw in that sine graph. the original function y equals sine of x. So at pi over 2, there's a maximum. At pi at 0, okay, right there. Okay, let's use key characteristics to graph this. Okay, first let's locate the sinusoidal axis. So that's y equals 1 because my d value equals 1. Remember, this is vertical displacement. So it's going to shift the entire graph up by 1 unit, which means the sinusoidal axis will shift up by 1 unit. So there we go. Okay, locate the sinusoidal axis at y equals 1. Done. Determine the max and min value. So let's use our formula from the previous page. Remember this part right here? Oops, this one right here. Handy formulas to remember, max and min values. I have a maximum value of d plus the absolute value of a, and that's 1 plus absolute value of 2, and that equals 3. Minimum is d minus the absolute value of a, that is 1 minus the absolute value of 2, and that equals negative 1. Okay, and then let's plot those. No, let's hold on to that for now. So that's a max at 3, a min at negative 1. Okay, so hold on to those now. Determine the period. B equals 3. Remember, we're in radians, so the period is also like our factor when we had those functions, right? It's 2 pi divided by the absolute value of b, so that's 2 pi divided by absolute value of 3, and that's 2 pi over 3. Okay, here's something new. Determine the values of theta for the start and end of one cycle from the function y equals a sine of b theta minus c plus d by solving the compound inequality. This value right here, so if I have my function y equals 2 sine of 3 times theta minus pi over 6 plus 1. Well, what are the elements that affect my phase or my period, my phase shift or period? Well, it's that middle part, the 3 theta minus pi over 6, or the b times theta minus c. So when I solve this compound inequality, right, I use the compound inequality. 0 is greater than or equal to b theta minus c is less than or equal to 2 pi, right? If b is 1 and c is 0, b is 1 and c is 0, I just get 0 is greater than or equal to theta is greater than or equal to 2 pi. And that's what we expect from a standard sine function for a period. But we have different values of b and c. So what we'll do is we'll plug them in. So 0 is greater than 3 theta minus pi over 6 is less than or equal to 2 pi. This is a compound inequality. So let's solve it. So I'm going to divide both sides by 3. So I get, so divide all sides by 3. That 0 is less than or equal to theta minus pi over 6 is less than or equal to 2 pi over 3. Well, there's our period right there, right? That's what we expected. Okay, we need to add pi over 6 to all the sides. Okay, plus pi over 6 plus pi over 6. So that's pi over 6 is less than or equal to theta, which is less than or equal to 2 pi over 3 plus pi over 6. That's 4 pi over 6 plus pi over 6. That's 5 pi over 6. Okay, put a box around that. Just going to put a box around some of the other key information here. Okay. So a note about this is these are the new boundaries for one period of our transformed function. Okay. Okay. Number 5, divide the interval into 4 equal segments, which gives 5 key values of theta along the sinusoidal axis. Okay, so let's do this. I'm going to just show you on what are my 5 key values here. 0, 0. This is pi over 2, 0. This is pi 0. This is 3 pi over 2, 0. And this is 2 pi 0. Okay. This is for y equals sine of x. Okay, so part A, instead of 0, theta, and then 2 pi, instead of this boundary, the period is now bounded initially by pi over 6 and 5 pi over 6. Okay, so part 1 is place 2 points for theta equals pi over 6 and theta equals 5 pi over 6 on sinusoidal axis. Which is y equals to 1. Okay, so let's do that. So let's go back up. So in red. Okay, pi over 6 is right here, folks. That's pi over 6. And I'm going to put it right on the sinusoidal axis. Okay, so that's the first one. And then 5 pi over 6, so pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6. I'm going to put the other one here. Okay. So I know properties of symmetry on my original graph, right? I have 4 basic sections. So take a look at the 4 sections that you create. So section 1, 2, 3, and 4. Okay? So between section 1 and 2, I know there's a maximum, right? So what I plotted so far was the 2 bookends right here. So right here and right here. That's just for one period, right? On the transform function. So this is Okay, so I know it's going to be divided into 4 sections. So I know I can plot, so part B here, your second point is the maximum value at pi over 3 or 2 pi over 6 and 3. Well, how do I know it's 3? Well, I know my amplitude is 2, right? Amplitude is 2. So how do I plot this? So next section up, here's the sinusoidal axis. Go 1, 2, and there's my amplitude of 2. Oops, sorry. So here at 1, I'm going up 1, 2, so that's my amplitude of 2. There's my second point. Letter C. Your third point is on the sinusoidal axis. Y equals 1. So let's go back up. Third point is right here. There's that section right there. See the lines I've drawn? Okay. Letter D. Your fourth point is the minimum value, 2 pi over 3, negative 1, or also 4 pi over 6, negative 1. Okay, let's show that one, the fourth point, right here. So pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, and then negative 1 down here. And then join it with a smooth curve like this. Okay, and that's how we graph this with key characteristics. And then you can just repeat the curve over and over again for 2 complete cycles. Okay, there we go.